Okay, so in this video we're gonna talk about the concentrations of solutions, and we will focus on the units that we use to calculate or represent the concentrations in solutions. Some of the units that we're gonna talk about are not very commonly used, and some of them are very widely used. And this is what we'll mention while we're talking about them. So the first one is the mass fraction, and from its name it is clear that it's a fraction. It's a ratio between the mass of the component I to the total mass of a mixture. So I have um, uh, two numbers. The numerator is the mass of the component of interest, and the denominator is the total mass of the mixture. Either it's 2, 3, 4, 5, 10 components, it doesn't matter, as long as I can know the mass of all of them. So X is the Mi divided by Mt, which is the mass of the component, and this is the total mass. And I can say that Mi is the Xi multiplied by the total mass, and of course the summation of the X is gonna be 1 at the end of the day, because it's all fractions. Summation of fractions will end up to be 1. And similar is the mole fraction, and we'd expect that this is, instead of the ratios of masses, it's ratios of moles. So it's the number of moles of component I, or the ratio of number of moles of component I to the total number of moles of the mixture. We put here the apostrophe just to differentiate between the mass and mole fractions. Both are x, but x dash is the mole fraction, and the x without the dash is the mass fraction. And again, the summation of x is gonna be equal to 1. It might be of interest to some people to know how to convert the values from mass fractions to mole fractions, and vice versa. So the x is the mass fraction, which is Mi divided by Mt. I can represent M as the number of moles multiplied by the molecular weight, and the same for the total mass. It's going to be the summation of masses, which is Ni Mi plus, or N1 M1 plus N2 M2. This is might be like 100 if you have 100 components. So this is not a big deal. So this is how we calculated. If we divide in numerator and denominator by Nt, the total number of moles, we will end up to have this as the mole fraction, and this is the mole fraction. So it's gonna be Xi dash, which is the mole fraction, multiplied by the molecular weight, divided by the summation of the mole fraction divided by multiplied by the molecular weight. So this is the relation that I can use if I know the mole fraction to get the mass fraction. So I can get the mass fraction as a function of the mole fractions. And we can do it the other way around. If I have the mole fraction is Ni divided by Nt, which is the mass divided by molecular weight, and this is the mass divided by molecular weight. And if I divide both sides, I mean the numerator and denominator, by the total mass, it's gonna be Mi divided by Mt, and the molecular weight, Mi divided by the molecular weight. This is the mass fraction, which is x. So it's gonna be x divided by molecular weight, and this is summation of x divided by molecular weight. So it's again a relation that I can use to convert the mass fraction into mole fractions, and vice versa. And this is a kind of nice example that we can use. It is I have a mixture of water, methanol, and ethanol. The water is 25 moles, the methanol is 35 moles, and the ethanol is 40 moles. So I can simply calculate the mole fraction, which is the number of moles divided by the total number of moles, which is 100. So it's gonna be 25 divided by 100, it's 0.25, 35 divided by 100, 0.35, and this 40 divided by 100 is 0.4. And I want to calculate the mass fractions. I know the mole fractions, and I want to get the mass fractions. I know the molecular weight, it's 18, 32, 46. And it's gonna be like direct substitution in this relation. I know the molecular weights and the mole fractions, and I will use this relation to calculate the mass fraction. So for water, it's gonna be 18 multiplied by 0.25 divided by 18 multiplied by 0.25, plus 32 multiplied by 0.35 and 46 divided by 0.4, and this is what I'm gonna get. 0.132 for water, 0.3228 for methanol, 0.54 for ethanol, and it's kind of simple and straightforward. But the point I want to make is to have kind of some sense of the numbers, because it's not just something that you calculate and you're done. You must have some sense of the numbers. I would see that here that for water it was 0.25, it's small fraction. Its mass fraction is 0.13, which is much less, it's almost the half. I have the ethanol here, the mole fraction is 0.4, but the mass fraction is 0.54, which is way higher than it was in the beginning. For methanol, it's not a big deal. It's not a lot of difference between 0.35 and 0.32. So just to understand why the numbers changed between the mass and mole fractions, think of them as like some sort of fruits. So the water is a small has small molecular weight. Ethanol has high molecular weight, so it's kind of like you have here like oranges. And these represent cantaloupe, and this represents watermelon, for instance. And these numbers, you have 25 pieces of orange, you have 35 pieces of cantaloupes, and 40 pieces of watermelon. So as a numbers, you know that this is 40 and this is 25. But as mass, the mass of watermelon is much bigger than the mass of oranges, and that's why as a mass fraction, the mass of the watermelons is gonna be way bigger than it was compared to the number of moles, and this or the number of parts or number of watermelons that I have. And this is why I would expect, even before I do any calculations, that the molecule that has, or the component that has higher molecular weight will have higher mole fraction, I mean mass fraction, than the mole fraction. This is the mole fraction, this is the mass fraction. The mass fraction is higher, and the molecule that, or the element that or I mean the compound that has smaller molecular weight, which is this, will have less mass fraction than the mole fraction. So this is something that you have to keep in mind, because if you do some errors in the calculations, you might get some wrong results. And by this quick comparison, you can check if your answer makes sense or not. Because if this is 0.4 and then you would find that it's 0.3, then something is not right. You have to recheck your calculations. We sometimes use, let's go to another unit, which is the volume fraction. It's not used a lot. I have never used it personally, and it is the volume divided by the total volume. We used it in the gases because it's almost equal to the mole fraction. But in case of liquids, it's not always right, but we can give it, or use it as an approximation, that the summation of volume fractions equals the total volume. Or I mean, this should be equal to 1. This should be equal to 1, the volume fraction, I'm sorry. Because this is a fraction, so the summation should be equal to 1. But this is not always right, but it can be like a good approximation. The units that we use a lot are these, the mass and the mole concentration. And this is the mass, or the moles per volume of the solution. And this is the CI, which is the mass concentration, the mass of the solute divided by the volume of the solution. And this is important to understand that this is two different things. This is the solute and this is the solution. In case of, because it might be confusing with the density. Density is the mass and volume, but the density is the mass and the volume of the same species. Water, its mass and volume of the same amount of water, or the water. But here you have the mass of the solute divided by the volume of the solution. And this is the other unit. It is the molar concentration. It's the number of moles divided by the volume of the solution. It's mole of the solute divided by the volume of the solution. This is very commonly used, and that's why it's called molarity. So once you say molarity, you mean that it is the number of moles per liter of the solution. So if I have it like 1 m, this is how we express the molarity. It is a solution with concentration of 1 mole per liter.
And it's needless to say that the relation between the mass and mole concentration would be the molecular weight, because it's just, this is the only difference, it's gram or gram mole. So this is how we, or these are the units that we use. I'm gonna stop here. In the next video we're gonna talk about the density of the solution. So I'll see you then.